Hi, everybody. My name is Lucas Latart, and I'm a fish biologist at the USGS Great Lakes Science Center, stationed at the Lake Ontario Biological Station in Oswego, New York. Today, I'm going to be talking about the Substrate Imagery project of CSMI 2023 that was used to evaluate lake trout spawning habitat in Lake Ontario. So for a quick presentation outline, we're really going to be going from start to finish on this entire project. We'll begin with some quick background information on lake trout and their status in Lake Ontario. Then we'll move into the sampling methods that we use to collect the different videos, as well as what the classification methods that we used to classify the different habitats was. Then we will move into the preliminary results of the study and what the implications of those results are for lake trout in Lake Ontario. Then we'll very quickly just look to the future on some future projects to help also assess lake trout in Lake Ontario. So to start off, you heard me talk about how this was a CSMI 2023 project. So what exactly is CSMI? CSMI stands for the Cooperative Science Monitoring Initiative, and it's an international effort that targets each of the Great Lakes on a 5-year cycle. So Lake Ontario was the CSMI for 2023. And this CSMI funding is able to provide a lot of larger projects that generally aren't able to be done on a regular basis because of the scale of the projects. For this project, the idea was to use ground truthing, so dropping cameras down to the bottom of Lake Ontario to evaluate the habitat composition for spawning habitat of lake trout. So just a brief project introduction. Lake trout were a historic top predator in the pelagic zones of Lake Ontario, but were extirpated in the 1950s. Since the 1950s, it's been a major management objective to try to restore a naturally reproducing population of lake trout in Lake Ontario, and the major method of this restoration has been stocking efforts varying from 300,000 to 1 million fish every year. Despite these stocking efforts, evidence of a natural reproducing population is limited. Recent lake-wide gill netting has shown that less than 1% of all of the lake trout caught were wild fish, meaning that the other 99% of the adults were stocked. So because there appears to be a limited success of natural reproduction in Lake Ontario, one of the hypotheses is that there are impediments present at the early life stages of these lake trout, so when they're eggs and when they're in their larval stage. One particular hypothesis is that spawning habitat in Lake Ontario has been degraded over time and is no longer viable for lake trout spawning habitat. It's believed that lake trout typically spawn between 4 meters and 15 meters in depth, and this habitat would be degraded by the infilling of key interstitial spaces between boulders and cobble that would incubate the eggs. So this project is an international collaborative effort between the United States Geologic Survey, the United States Fish and Wildlife Service, the New York State Department of Environmental Conservation, the Ontario Ministry of Natural Resources, and the Department of Fisheries and Ocean. There were 5 agencies, a handful of vessels, and dozens of video collectors that helped to make this project possible. The goal was to collect habitat data across the entire shoreline of Lake Ontario between 1 and 30 meters of depth, and then to classify these substrates to try to identify areas where quality lithophilic spawning habitat, so spawning habitat for lake trout, could be found. So site selection was done by Colin Farrell at the U.S. Fish and Wildlife Basin Office using Alex Gatch's max ent model for lake trout spawning habitat. So sites were selected across the Lake Ontario shoreline between 1 to 30 meters of depth, and there was a total of 3,000 sites selected. Each site would then get 5 individual camera drops, so 5 individual videos that were roughly 5 to 15 meters apart. And the reason why we wanted to collect 5 separate videos was just to reduce the bias that one video would give you. You know, if the camera landed on a boulder, but the boulder was in the middle of nothing, we didn't want to classify that habitat as a boulder when really there's nothing around it. and to also provide us with just a finer project resolution of the lake as a whole. The image on the right will give you a pretty good idea of how our equipment was set up to record. We had a vertically oriented camera that was affixed to a steel cage with a cable running all the way up to the vessel with a live feed of video that could be recorded. The camera was placed into the cage for a variety of reasons. It was to protect the camera from being bounced around on any of the hard substrates down there because these cameras are pretty fragile. It helped to provide a sense of scale, to classify the different sized substrates, and depending on how far the cage sank into the lake bed, you could tell how much silt was present at the site. So now a quick demonstration of how videos were taken. We would first roll up to a site. We would then drop our camera all the way down to the bottom. After we were happy with the recording, we would pull it about halfway up to save the shoulders of whoever was pulling the camera. We would then move the 5 to 15 meters to our next video drop location. And we would drop the camera again to the lake bed. And we would repeat that until we had our 5 videos at the site. So now that we have all of our videos, we can start classifying the substrates. We used an adapted version of the Coastal and Marine Ecological Classification Standard, or CMEX, as I'm going to refer to it in the rest of the presentation. CMEX is essentially the standard across all of the Great Lakes for habitat classifications. And we slightly adapted it to better fit the goals of our project. Essentially, we classified a dominant, so greater than 50%, and a secondary, less than 50% substrate type at each video site. We also added a number of variables that we scored from 0 to 4, so interstitial spaces, the thickness of the silt at the site, the amount of biotic vegetation, if there was any, and then the confidence value, which was how confident the interpreter was of their classification of the substrates at the site. So that table on the right will give you a better idea of how we were classifying the substrates. There were 7 subgroups in total, 5 of which were geologic, which were bedrock, boulder, cobble, pebble, and fines, and those are shown there from largest to smallest. Then there were also 2 biogenic subgroups, which were muscle hash, which is dead Dracaenan mussels, and muscle reef, which are live Dracaenan mussels that are still attached to the substrates on the lake bed. It's typically believed that boulder and cobble are kind of the preferred spawning habitat for lake trout because they can provide a greater quantity and quality of interstitial spaces, whereas smaller substrates like the fines, the Dracaenan mussels, and the muscle hash are going to be poorer because they cannot provide the same quality of interstitial spaces for egg incubation. So throughout this project, we kind of saw the good, the bad, and the ugly situation come forward with the different substrate types that we had. The good, where there were large boulders and large cobbles stacked on top of each other, where there were a vast abundance of really deep interstitial spaces that an egg would have lots of protection in for its incubation period. Then we had the bad, which was these fines and kind of bedrocky habitats that are just flat. There's really no interstitial spaces there that can help to protect the eggs. And then the ugly, which are these mass deposits of dead Dracaenan mussel hash, or in many cases live Dracaenan mussel reefs that have overtaken the lake substrates at given sites. So getting into the results of this survey, here's a figure that's a box plot showing depth on the y-axis. The y-axis is actually inverted, so 0 depth at the surface is on the top, and then 30 depth is at the bottom, which is kind of our cutoff point of the survey. And then each of the different 7 subgroups is shown here. And kind of the pattern that you can see is that boulder and cobble, which is really this kind of good substrate that we think lake trout like to spawn at, is really only frequently found between 5 and maybe 8-ish meters in depth, with some less frequent occurrences down to about 12, and then the outliers really start popping out deeper than that. And then there were no boulder or cobble found deeper than 20 meters in depth in this survey. whereas substrates like fines could be found all the way down to 27 meters and were found at virtually all depths. So what you're looking at here is the results of our multinomial logistic regression model that is serving to predict the probability of occurrence for each of the 7 substrate types at given depth. As you can see, kind of the cobble, which is green, and the boulder, which is that orangey color, what we think are preferred lake trout spawning habitat, are most common in shallower depths and then become less common as depth increases. At 10 meters in depth, there's only about a roughly 7-8% average probability of occurrence, and then decreasing even further to hitting roughly 0% probability of occurrence at maybe 17-18 meters. This is important because these are the 2 substrate groups that we are expecting to provide these interstitial spaces that are key to lake trout spawning for egg incubation. Inversely, fines, which is the gray line there, is not very frequent in shallower depths, but becomes very frequent, nearing 75% probability of occurrence at roughly 30 meters in depth. And this is important because fines are not expected to provide interstitial spaces that could be useful for lake trout eggs. So this figure here is similar to the box plot of the substrate types, but is instead showing our 5 interstitial grade with depth. So again, depth is that y-axis, 0 at the top, 30 at the bottom, and then our 5 substrate groups. For context, 0 interstitial score is flat bottom, nothing there, no interstitial spaces. And whereas 4 is, think of those pictures under the good, right? So really high quality, abundant interstitial spaces, great egg incubation habitat. We really think that lake trout would like to spawn there. These interstitial 4 substrates are really only being found between 5 and maybe 7 meters in depth very frequently. The deepest that they were seen was just past 15 meters in depth. Interstitial grade 3, which is also good habitat, just not kind of best of the best, is frequently seen between 5 and 8 meters in depth, and is more common than interstitial grade 4, but still very uncommon. Interstitial grade 4 and interstitial grade 3, their total combination was only 6% of all of the video drops of this entire survey. So this figure here is another result of a multinomial logistic regression model. Again, this time instead of substrate type, we're looking at our 5 interstitial scores. The key to this figure is really that interstitial grade 4, which is the red, and the interstitial grade 3, which is the orange, generally speaking, have a very low probability of occurrence, but it only gets worse with depth. At 10 meters, our interstitial grade 4 has a near 0% probability of occurrence, and our interstitial grade 3 has a maybe 5% probability of occurrence at 10 meters. And this is important given the historical context that we believe lake trout spawn between 4 to 15 meters in depth. This would mean that about 50% of that habitat between 10 to 15 meters has really just doesn't have the quality interstitial spaces that could be used for lake trout egg incubation. So for some more results, this figure on the right here is showing all of the drop cam video sites that were taken. We layered this map so that the higher interstitial scores would overlap over the other interstitial scores. And the reason that we did this is because there's so few that if we didn't layer it this way, you would not be able to see where the interstitial grade 4, interstitial grade 3, etc. sites are on this map, because they would just be covered by interstitial grade 1s and 0s. In total, across the 5 agencies, 7,143 videos were collected, which is pretty insane. And of that, 6,964 were of high enough quality to classify. Of these 6,964, though, only 92 had grade 4 interstitial spaces, which is roughly 1.32% of all sites. Again, very low percentage of what we consider to be that excellent spawning habitat. The 3 most common substrates were fines, mussel reef, and mussel hash. Again, kind of reinforcing that habitat degradation that is occurring in Lake Ontario. And I'm running out of time, so I'll go through the rest of these pretty quick. The highest density of interstitial spaces score for substrates that we had were between Rochester and Oswego on the southern shoreline. These had the 3 survey units with the highest percentage of grade 4 interstitial spaces, as well as the 3 survey units that had the highest total number of grade 4 interstitial spaces. This is likely just due to those strong northern winds coming over and just clearing out interstitial spaces between these cobble and boulder that are found there. Degradation due to silt is pretty apparent from this survey. We found that 90% of all sites had some amount of silt present. Habitat degradation due to invasive mussels was also apparent. Mussel hash was present as either the primary or secondary subgroup at 50% of all of our sites. Likewise, mussel reef was present at roughly 45% of all of our sites. So I already mentioned this, but probably the most important finding of this survey was that once you get past 10 meters in depth, you're very unlikely to find quality lake trout spawning habitat. This is because of the low probability of occurrence of boulder and cobble substrates and the very low probability of occurrence of grade 4 and grade 3 interstitial spaces. So for the implications, as I had mentioned earlier, roughly 50% of that historic lake trout depth range of 4 to 15 meters likely isn't viable because of a lack of interstitial spaces. There was a clear degradation due to sediment infilling by silt, as well as the presence of live and dead dracaena mussels. And without these quality interstitial spaces, egg incubation is less successful, meaning spawning overall is less successful. And then really quickly, just for moving forward, this project was kind of just a course overview of the Lake Ontario shoreline, and it's important in the future to get a more fine scale resolution of these areas that had quality interstitial spaces. The areas in the lake that did have high quality interstitial spaces, it's important to conduct more research on spawning itself, both looking at egg deposition and larval emergence. This image on the right here is an example of a project done at USGS Labs in the fall of 2024 to try to pump for lake trout eggs to try to find where they're spawning at in Lake Ontario. And this is just another image of kind of the crew in action. Our most successful site was out on the artificial reef Olcott Shoal in western Lake Ontario. And here, this is the drainage basin of our egg pump, and you can see, or maybe can't see, inside those red circles are actually lake trout eggs that we had successfully pumped up from the lake bottom. It's pretty cool. On top of this, it's also important to check greater depth ranges. So this study capped out at about 30 meters, but in other Great Lakes, there are known lake trout spawning reefs that are much deeper than 30 meters, such as Mid-Lake Reef in Lake Michigan. Additionally, there is a USGS data release for this project, as well as a journal manuscript that is currently in internal review. Just a really quick acknowledgement to the Great Lake Restoration Initiative and the Sea Grant for funding this project. I'm already way over time, so I can't go through all of the individual video collectors, but if you see your name on this list, just know that this project would not have been possible without you. Thank you so much for your effort in collecting these videos. And unfortunately, I'm not there to field any questions, but if you did have any questions about this project, feel free to email me at lletarte@usgs.gov. That's LLETARTE @usgs.gov. Thank you.